everyone. This is part 2 of our lesson on evaluating limits algebraically. Okay, we just had all of our fun that we could possibly have with factoring and with rationalizing, and now we're going to do some trigonometry. Okay, but we're going to cheat a little bit here. So I'm starting you out with these trig functions, and these are probably not trig functions you've seen before, but these are ones that tend to come up a lot in limit situations, and both of these are indeterminate. Okay, I know that because if I put a 0 in here, sine of 0 is 0. So then I end up with a 0 over 0, that's indeterminate. This one, cosine of 0 is 1, and so 1 minus 1 is 0, and then I get a 0 over 0 as well. Okay, and we'll talk about this one in a second. This one's not a trig one. We've actually talked about this one already. So these are the two I want to focus on first. We don't have a good algebraic way to solve these. There might be some way out there that you can do it with trig identities or something like that. There is a way to solve them that we will learn later in calculus, but we have to learn derivatives first, and we haven't learned that yet. So for right now, our only option with these two guys is to look at them on a graph. Okay, so we're going to look at them on a graph, and I'm going to encourage you to memorize the answers to both of these. And I know that seems like a lot. Later in the course, you're going to learn how to actually solve these so you won't have to just rely on memory anymore. But for the sake of these problems that we're about to do, you will want to know these two examples. So I'm going to get rid of these ones that we looked at in our last video. And I'm going to look at sine of x divided by x. Okay? And we've got this graph that, oh, why did I just do that? Okay, beautiful. We get this graph that looks something like this. We may even want to, well, we could mess with this graph a little bit and adjust it to be, focused on trig values, but what we really care about is what's happening at 0. And if we look right at 0, I believe we're going to see that it's undefined. Right at 0. There it is. Yep. Okay, so right at 0, we're undefined. But if you take a look at what's happening immediately to the left and immediately to the right, and actually I'm betting this is just because of rounding, it looks like you actually hit 1 a little bit before and a little bit after. But this limit value, if we zoomed right in on that, both sides are approaching 1. Okay, like if we looked at the horizontal line y equals 1, you can see that the purple line is climbing up towards the red line. Like that's where they're going to intersect. Okay, so this limit here, as x approaches 0, is always going to be 1. Let's look at our other one. 1 minus cosine x, and then all of that divided by x. Okay, and if you notice this one, as we're approaching 0, again, right at 0, we're undefined, but the value that really should be there, like if we were going to plug that hole, should just be 0, 0. Like if you look at how tiny these values are, and then as soon as I get to 0, I'm undefined. Okay, so this limit is always equal to 0. And those are going to be important as we do some of our examples down here. I actually think, I kind of wish I had done this in a different order. I'm going to skip over this for right now, and I'm going to skip over these first 3 examples because these all go together and they go with this. I want to try one of these trigonometry ones. So let's try this bullet point right here. Okay, so first thing I would do, and you can write this down if you want to, or this is something you could just crunch numbers in your head. So if I take 0 and plug it in up top here, I get 3 times 0, so that makes a 0. This is going to make a 0, and then sine of 0 is also 0. So 0 plus 0 minus 0, that whole top's a 0. And then, of course, it's over x, so that is also 0. So this one is, we've verified, indeterminate. Which, the weird thing is, indeterminate functions don't happen a whole lot algebraically. But they're the ones that make you have to do the work. And so as we're trying to teach these to you, we're not going to just throw a bunch of boring ones at you. These are the ones you're probably going to see the most often because this is like the new skill that you're learning. So you're going to see me start to go into a lot of these with sort of a like, well, of course this is indeterminate type attitude. And we really should be taking the time to check, right? We should put the zeros in and make sure that this thing does actually equal that. So I need to take this expression and do some stuff to it, okay? And what I'm going to do is I'm going to, and I don't know that you would even need to write this down realistically, but I'm going to take this and divide each one of these pieces separately by x. So I'm going to have like 3x over x plus 5x cubed over x. Whoops, that's a minus. So minus sine x over x. Okay, and what can happen here and here is, here for example, these x's go away, and then here x cubed over x, one of those x's is going to cancel, so I'll have an x squared, and that'll cancel with this x. This one I can't get anything to cancel, but I know this limit from up above, okay? So I'm going to now take my limit and rewrite it and say this is the same thing as taking a limit as x approaches 0 of 3 plus 5x squared. Whoops, I did it again. Minus sine x over x. Okay. Remember that from properties of limits, when I'm taking the limits of a bunch of things added together or subtracted, I can just take the limit of each piece individually and then add or subtract the limits. So if I do the limit as x approaches 0 of 3, that's just going to be 3. Because think about this. If you just had this, okay, that's like the function y equals 3. That's just a really boring horizontal line. So y is always 3. So if I'm asking you the question, hey, what's happening to y as x is approaching 0? It's 3, because it's always 3. So when you're taking the limit of a constant number, that is just your limit, that number, all the time. So that's a 3. Now, for the 5x squared, that's going to be like plus 5 times 0 squared. And I'm writing that out so you know what I'm doing. I'm putting the 0 in there, but that's really just going to make a 0 and disappear. And then the limit as x approaches 0 of this thing from up above, and I keep pointing, I know you can't see it, it's off screen, but it's the first thing we wrote down, is this limit is always equal to 1. So then I can just say this is minus 1. So now I have 3, this is really 0, minus 1, and so my answer here should be 2. Okay, that's how these are going to work. This situation is going to pop up quite a bit. This sine of x over x, the cosine one happens a little less often, but it still shows up from time to time. And then when you see it, you can just be like, oh, I already know the answer to this one. Okay, I want to tell you this last example on this page is a really, really difficult one. It's a really tricky one. I don't want to take up your time in the video working through it. Even in class, I'm going to kind of have it as a bonus question. But what I will do is at the end of this video, I'll pop in and just show you what this work looks like so you can see if you can try to work it out on your own. So if you do want to pause the video and try that one, you certainly may. There's a lot of algebra trickery in there, but we'll see where you get. Let's go back and talk about this absolute value thing. You've seen this before, okay? This function, x minus c over x minus c, where one of them is an absolute value, and you could actually have the absolute value on the bottom as well. This is always going to end up looking like this. You're going to have a horizontal line here, and this is at 1. And then you're going to have a horizontal line here, and this is at negative 1. Okay? And the reason for that is the top and the bottom of this thing are always going to be equal to each other. And when you divide two things that are equal, you're going to get 1. Except when you have numbers, for example, that are smaller than your c value and you try to subtract, on the bottom you're going to get something that's negative. But with those absolute value bars on the top, that's always going to come out positive. So you're going to have two numbers that are the same value, but sometimes the bottom will be negative and sometimes it'll be positive. Well, the top is always positive. So this break in the graph that I kind of drew in here, this is always going to happen at whatever that C value is. Okay, so this number here, that's where this graph is going to break. There's going to be a discontinuity. You actually end up with a 0 over 0 here. But this is someplace where the limit truly does not exist. Okay, even though it would come out indeterminate, the graph looks like this. We've got two limits. The limits from either side are not equal to each other. Okay, so these three kind of all go together. Notice that this one is asking you to think about the limit as we approach 4 from the right. So 4 from the right, that's thinking about numbers that are bigger than 4. Okay, so think about plugging in a 5 or a 6 or a 7. I'll just use 7 since I landed there. 7 minus 4 is 3. 7 minus 4 is 3. 3 over 3 is equal to 1. And that's going to happen no matter what number you put in here. You're always going to end up with a positive 1 if you're choosing numbers that are bigger than 4. Okay, that's this piece of the graph. Okay, where you're at 1 no matter what. If you pick a number that's smaller than 4, so let's say you pick 1, because 1 is smaller than 4, that's to the left of 4. 1 minus 4 is negative 3, but those absolute value bars make it a 3. Over 1 minus 4 on the bottom is negative 3, so then I would have 3 over negative 3, that makes a negative 1. Okay, so limit from the left, limit from the right, because that's this part of the graph. So then when I just ask you the overall limit, your answer should be, this limit does not exist. Because in order for the limit as x approaches 4 to exist, the left and the right have to be the same. And because they're not equal, that's why this doesn't exist. You've actually done this same problem like a jillion times. So this is just where it shows up formally in the notes. So I do want to jump back to the first page of these notes and talk about that tangent example. So give me a second to shuffle papers here. Okay, so on the first page of this notes, you had an example where we were looking for, oh, I guess I could have had this written for you before I restarted the video, sorry. A limit as x approaches 0 of tangent of x over x. Okay, and we did figure out that it was indeterminate, because if you put 0 in here, the top is 0, the bottom is 0, indeterminate. So we've got to work some magic here. Okay, what I want to remind you is that tangent of x is actually equal, let me rewrite my expression here. Tangent of x is actually equal to sine of x over cosine of x. But I still have this x on the bottom, so I'm going to leave that on the bottom with the cosine. So tangent became sine over cosine, and then this x is still here from my original expression. And then I'm going to split this thing up. I'm going to make this sine of x over x, and then let's just pretend there's like a 1 here, because, I mean, there is. And I'm going to put these two together, 1 over the cosine of x. So I'm going to rewrite this thing as sine of x over x times 1 over cosine x. Okay, let's see how that works for us. So if I say that this limit is the same thing as the limit as x approaches 0 of, probably don't actually need the parentheses there, but sine x over x times 1 over cosine x, and now I put the zeros in. I don't actually want to plug the 0 in here, but I know this limit, right? The limit of this thing, sine of x over x, as x approaches 0, we said was 1 times, and then here we have 1 over cosine 0. Okay, think about cosine 0 there for a second. Cosine 0 is just 1, so this becomes 1 times 1 over 1, and that whole thing just works out to equal 1 as a final answer. I'm going to verify for you, because that one might feel a little bit like magic, but here's our function, tan of x over x, and as we're approaching 0, look where your y values are landing. Your 0 is undefined, okay, but on either side you can see your y values. Now they're both kind of coming down from the top, but they're both getting closer and closer to 1. In fact, I mean, look right there. You're awfully close to 0. Y values are equal to 1. Okay, so that's one way that you can use this sine of x over x function to find some limits. Okay, I am going to pause my recording of the video. You may want to pause the playing of the video. And I'm going to work through this last example here, and then I will pop back in and show it to you. Again, this is a big stretch, so if you look at this last example and you're like, ugh, I don't have a clue, we'll talk about it a little bit in class, but I would not stress about it too much. Okay, movie magic there for you. I'm going to kind of talk you through the algebra that I've done up to this point. And again, I would hope that you could at least follow the steps I'm about to explain to you. Maybe you wouldn't have thought to do them on your own, but I hope you can follow. So I took this expression. It's got this lonely 4 sitting here. First thing I did was factor out a sine x. So I see a sine x here and a sine x here. So I pulled out what they have in common, and what was left was a cosine x minus 1. That looked really familiar to me. Okay, that looked like one of the expressions that I know to work with, except it was the other way around. I really wanted this to say 1 minus cosine x. So technically what I did here, this is a math trick with subtraction. I factored out a negative 1. I divided this and this both by negative 1, and that flips your subtraction. And then I took that negative 1 and I attached it to the 4. Okay? So I factored it, like I divided both of these by a negative 1. Picture me putting that negative 1 out in front here. But then I just took that negative 1 and combined it with the 4. So that's why this turned negative. Okay? And then what I did is I said, well, there's actually 2 x's down here. So I do want to split this into 2 expressions. But I'm going to put 1x here and 1x here. And that's what you see me doing here. I have a sine of x over x and a 1 minus cosine x over x. Okay? And if you put those back together, you would get your x squared back. So now, I can technically say that this limit up here is equal to the limit of this new expression. So limit as x approaches 0 of negative 4 times sine x over x. This one, when we get to the end of it, is going to feel like, man, why did we do all this work? Because it works out so easily at the end. Okay. Okay, so this first limit's just going to be a negative 4 times sine of x over x, as we're approaching 0, is 1. Okay. And then remember this one from the other page, 1 minus cosine x over x, and by other page I actually mean the top of this page. That limit is just equal to 0. And so this is what I mean, is as soon as I get that 0 in there, this whole limit just turns into a 0. Which feels like a lame answer, but at least it's an answer, right? It's not indeterminate anymore. We can find the actual limit. So this one was a pretty tough one. I would not be too stressed about that one, but I would say something like this one up above. Totally fair game. And you will want to be able to recognize these trig values when they pop up. Okay, I think that's everything for the rest of this lesson. We're just going to practice a whole bunch of these now. And we'll talk about some more in class, I am sure.